Let's solve this question. Consider a simple series RL circuit where the input is the voltage and the output is the current IT. So what we're trying to find here is the mathematical modeling of this circuit. First, let me draw out the circuit so we can see it clearer. So what we're going to do is to find the KVL of this circuit. KVL is Kirchhoff voltage law, which states that the sum of voltage in a loop is equal to 0. Taking the KVL, we have V of t minus V of R minus VR of t, minus VL of t is equal to 0. And that is because of, let's say, this is your positive, positive, positive. This place is a negative. That's how we derive this. Making your VT the subject of formula, all this will come back. Yeah. So your VT now be equals to VR of t plus VL of t. Now you need to find what is your your voltage of your resistor and voltage of your inductor. The voltage of your resistor from Ohm's law, V is equals to IR. That's VR of t is equals to your resistor multiplied by your current. And your voltage, the voltage across an inductor is equals to the value of your inductor multiplied by the differential of the current flowing through the inductor. So knowing this, we will now have your V of t equals to RIT plus LDI dt. So this is your first order linear ordinary differential equation. So we have another example right here. Consider a simple series RC circuit where the input is the source voltage V in and the output is the capacitor voltage V out. So let me draw out the circuit so we can understand it. So to find the mathematical model of differential equation of this circuit, we are going to use KCL, that's Kirchhoff current law. So we are taking this as our node. So we have this Kirchhoff current law states that the current flowing into a node must be equal to the current flowing out. So this must be equal to this. So to calculate the current flowing through the resistor, okay, so the current flowing through the resistor will be your V in minus V out for your R. So the voltage here minus the voltage here divided by a resistor, that will be V in minus V out by your resistor. It will be equals to the current flowing through this capacitor, and that will be your capacitor multiplied by the differential of the voltage flowing through the capacitor, and that is your V out of t over your dt. And making your V in subject of formula, cross multiply, that will be V in minus V out plus RC differential of your V out over your dt. Then your V in will now be equals to your RC differential of your output voltage over your dt plus V out. So this will be. Let's take a look at this example. Consider a series RLC circuit where the input is the source voltage VT and the output is the voltage across the capacitor Vout. So to find the um, ODE of this circuit, let me draw the circuit. So to analyze the circuit, we're going to use Kirchhoff voltage law, where we have your positive, yeah, positive, 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 and negative. So solving for the V here, we are going to have your VT, VT minus VR of T minus VR of T minus VC of T equals to 0. So making your VT subject of formula, your VT equals to VR of T plus VL of T plus VC of T. Oh, now getting the voltage of each of these components, we have your VR, the voltage across your capacitor will be equals to, from Ohm's law, your resistor value multiplied by the current flowing through it, while the voltage flowing through your inductor will be equals to your value of your inductor multiplied by the differential of the current flowing through it, and your voltage of your capacitor will be equals to 1 over the value of your capacitor multiplied by the differential of multiplied by the integral, sorry, of your current of the current flowing through it. So putting this into the equation, we have VT you have your VT of T equals to R dot your current plus your inductor multiplied by the differential of the current flowing through it plus 1 over C integral of your current dt. So to resolve this, we're going to differentiate this right here. So differentiating your VC of T, we have dv C of T over dt now be equals to your 1 over C I of T. So because the differentiation will cancel this integration. So differentiating it again, you have your d square VC of T over dt square equals to 1 over C d I over T dt. So from here, we can make I of T subject of formula. That will give us I of T will equals to its capacitor multiplied by differential of Vc of T over dt. And over here, we can make your di dt subject of formula. So your di dt will be be equals to your C multiplied by over your dt. So substituting these values inside the equation that we have. Let me go down so that we have more space. Vt equals to your R multiplied by, what's our I of t? That will be C d Vc of t over dt plus your inductor multiplied by, what's your di dt? That will be C capacitor d square V C of t dt plus Vct. So from here, your V of t will be equals to your RC dVc of t over dt plus LC d square Vc of t over dt plus your Vc of t. Dividing through by LC to remove the constant from your, sorry, I made mistake here. I meant to keep your square. Yeah, sorry about that. So to remove the constant of your second order differential, you divide through by LC. So dividing through by LC, you have t square Vc of t all over your dt square plus your RC all over LC. That will give you R over L. But dt plus 1 over LC Vc of t equals to also 1 over LC V of t. So this is your final answer. We have another example right here. Find the transfer function of your V out over V in for the RLC circuit above. Take the Laplace transform of the differential equation, assuming zero initial condition. So let me write out the equation. Okay. Convert this to Laplace transform. You know that your d square Vc of t over dt square will give us a square Vc of it, and your v your tc of t over dt will give you s Vc, yes, and your Vc of t give us Vc of s, and your Vs of t give us Vs of s. So substituting this into the formula, we have LC s square Vc of s plus your RC Cs Vc of s plus Vc of s equals to Vi of s. So your transfer function g of s equals to this right here, Vc of s all over Vi of s. That will be equals to, before that, let's just to make it easier, let's factor out I will have VC of S first before doing anything. VC of S, open brackets, big brackets, LC S squared plus RC S plus 1 equals VI S. So solving this, now have your all over 1. So this is your transfer function. This example, we have to find the pole to zero map of the transfer function. So first, we have to know that your general form of your transfer function g of s is equals to k s minus z1 s minus z2 plus s minus zn over s minus p1 s minus p2 plus s minus pn. So where your z1, z2, zn are zeros, and p1, p2, pn poles. And also note that your number of poles will always be greater than the number of zeros. So comparing this with the equation you have here, so we know that our poles are above our zeros. So we have g of s equals to, let me write out the equation. So our zeros will now be equals to our zeros be s equals to 2 from this one right here. Your s equals to minus 2 minus g for s equals to minus 2 plus g for your poles. You have s equals to 3, s equals to 4, s equals to 5, and your s equals to minus 1 minus g5, and your s equals to minus 1 plus g5. So I hope you understand how we got this. So to draw the poles and zeros map, for your zeros, this is you represented by this symbol. While for your poles, you represented by this. Let's draw the map, and let's draw the graph. So to represent our zeros, we have x equals to minus 2. Circle this. And s equals to minus 2 minus g4. So this is your s-plane. This is your imaginary, your omega. So we have 0 is minus 2 minus g4. That will be, we trace it up. Trace it down. Minus 2. So we have this. Then minus 2 plus g4. Then for your poles, that's all for 0. For your poles, you have s equals to 3, s equals to 4, s equals to 5. Then we have s equals to minus 1 minus g5. I forgot to add g5. Minus 5. So we'll trace it here. Then we trace this on some. So this right here is your pole 0 map. That's your final answer.